So this is lecture number 6 of this business process mining course. Today we are gonna focus on the topic of how to use process mining to analyze the performance of a process, an approach that we usually call process performance mining. The course outline is given here. We are pretty much in the middle of the course, currently touching into performance mining and variant analysis, which is the topic that we're going to cover. And then we're going to move next week into more advanced topics such as simulation and what-if analysis, and then data extraction and other important topics in process mining. So with respect to the 4 capabilities of basic process mining, we are pretty much wrapping it up this week. I'm going to talk about performance mining, and I'm going to relate it back to variant analysis, which is a topic we started to discuss last week. In terms of the workflow for analysis of the process that I presented to you last week, we have started a couple of weeks ago with this automated process discovery phase. So which is like the first thing you will do when you get an event log and you want to understand your process. And last week we saw this part, compliance checking, identifying deviations with respect to compliance rules, and how to then split the event log into compliant versus non-compliant cases and use variant comparison techniques in order to understand what distinguishes these 2 types of cases. This week, we are going to move on the right-hand side of this workflow, and I'm going to be talking about techniques that you will use when the emphasis of your analysis is on understanding the performance of the process, particularly the bottlenecks on the potential sources of waste. Before I dig into the topic of performance, process performance mining, it's kind of important to recap some of the concepts of process performance measurement that we kind of introduced, we saw a few weeks ago when I spoke about performance dashboards, and that we're gonna go deeper into this during this lesson. The mother of all measures of time performance in a process is the cycle time. And I remind that the cycle time is the amount of time between the moment a case starts and the moment a case completes. If I take a process observed during a period of time, say 1 year, the cycle time is the average of the cycle times of the instances that completed during that period of observation. Please keep in mind that maybe to make things a little bit more complicated, in the field of process mining, instead of using the term cycle time, the tools usually often use the term case duration, because the basic unit of analysis is the case, and a case has a duration from the start to the end. So it's just so convenient to just call it case duration instead of cycle time. Now, we saw a few weeks ago that the cycle time of a process includes 2 things, or is composed of 2 things. The time that we spend actually doing work and the time that we spend in between 2 activities in the process. So the time that we spend waiting for an activity to start. The first one, the time that we spend working, doing activities in the process, actively putting time into the process, that is called processing time. And the time that we wait, that is called waiting times. And in theory, waiting time plus processing time is equal to the cycle time. We also saw that there is a very important measure of efficiency of a process called cycle time efficiency, which is simply the processing time divided by the cycle time, meaning the time we spend actually doing work in the process, actively working in the process, divided by the whole duration of the process. That is a number between 0 and 1. 1 meaning 100% of cycle time efficiency, which is unattainable, means that I start the process and I work, and I deliver to the customer done. But in practice, it doesn't work like that because, of course, we are not only doing work for one customer, we are typically handling many customers. Our workers are not machines. You know, they cannot just like continuously work nonstop without breathing. There are context switches, there are handoffs, and for cost efficiency purposes, we do not have enough people to actually be actively working on every customer case at all points in time, 24/7. Therefore, the time that the case takes, the cycle time, will typically be longer than the time that we are working on it, the processing time, and therefore the cycle time efficiency will be not 100%, but maybe 10%, 20%. 10% is actually considered to be already pretty good, but of course, companies will strive to have higher cycle time efficiencies, particularly for their customer-facing processes. The second performance dimension in the field of BPM is the cost dimension. And we saw that let's say the most entry-level measure of cost in business processes is the per instance cost, the cost of executing one instance of the process. And that theoretically, if we analyze it, this cost can be decomposed into the processing cost, the cost of doing value-adding steps in the process, plus the cost of the waste. For example, the cost of correcting defects that we commit during the execution of a process. Cost can usually be decomposed into 3 dimensions: the resource cost, the cost that the resources consume me, the material cost, which is the cost of the products I am shipping to the customer or of the raw material I use to produce the products that I ship to the customer, and the compensation cost. In the field of BPM, as a process manager, I'm typically foremost interested in reducing resource cost. But of course, material costs and compensation costs are very important concerns in operations management. The third dimension of performance is the quality dimension. And in there, we find different types of measures. One of them is the defect rate, and we're gonna be trying to analyze defect rates by means of process performance mining. The defect rate means that you will define conceptually. So you have to analyze the domain and you have to come up with a notion of defect. For example, in an IT help desk process, the fact that I close an issue as resolved and later I reopen it because it was actually not fully resolved, that is a defect. The percentage of cases in this process where issues are reopened, that is the defect rate. A defect rate of 10% in this context means that in 10% of cases, the issue is reopened. The second type of performance measures that you define, that you manipulate, is the delivery quality. One measure that we'll be particularly analyzing is what we call the on-time delivery rate, the percentage of instances of a process that meet a certain performance goal. That could be, for example, that the cycle time of the process must be less than 2 days between the moment a ticket arrives in the IT help desk and the moment it is resolved. No more than 2 days arrive. And in a typical IT help desk, I'm going to have performance targets. Like, it should be the case that at least 95% of tickets are completed in less than 2 days. In some contexts, I'm also interested in analyzing the mean execution time of my cases. And I want to make sure that most cases are within a small range. That's something we will try to analyze. We'll try to look at the variations in the cycle time and make sure that there are no wild variations. It's not very good when some cases are taking me an exaggerated amount of time. And finally, the third measure of performance is the external quality performance, usually measured by means of customer feedback scores or so-called net promoter scores, or NPS. You know, how satisfied your customers are and how likely it is that they will recommend your product or your service to others in their network. So process performance mining is about using process mining techniques to analyze the process in terms of performance measures, such as the ones that I just introduced to you. And to do this, we are going to use 4 main types of operations: duration-enhanced process maps, duration-enhanced BPM and models, log animation, and performance dashboards, in order to answer or to conduct 4 types of analysis tasks. So we use these 4 capabilities of the tool to perform 4 types of tasks. Bottleneck analysis, where we focus on finding bottlenecks in the process. Workload and demand analysis, where we focus on understanding how busy we are. Rework analysis, where our focus is on finding how much time are we spending redoing things and why are we doing that. And over-processing analysis, where we are trying to find activities that we are executing and that we shouldn't be executed. So over-processing is a type of waste that we will try to reduce in our process. Let me look first at a bottleneck analysis. To perform bottleneck analysis, I will go to my process discoverer. I will use the process discovery functionality of process mining, and I will put a duration overlay. I have to be careful, of course, when I choose what kind of metric I put on top of it. Bear in mind that, you know, by default, you will put average durations on top of the process map when you overlay the durations, but averages are sometimes not very good. If the distributions are very skewed, maybe the median is better. And sometimes you might want to reason in terms of the total effort, because an activity might have a high average or median execution time, but it might be very infrequent. So the total amount of time you spend on it is maybe not too high. But assuming that you have selected a duration overlay with a certain aggregation function to it, then the duration overlay will allow you to find the activity weighting bottlenecks, those activities such that the waiting times leading to those activities are the highest. So when you do duration analysis, when you do bottleneck analysis, the first thing you want is to find that activity that has the largest waiting times leading to it. The second thing you will try to find is those activities that take the largest amount of processing time. So let me show it to you in the tool. I'm going to take, for example, an event log of the production process. No, I have here. Production process, which is an event log I have been using as a running example, which is an event log of machines in a factory that and production batches that are going through these machines. The process starts with some turning and milling through different machines. Sometimes there are some issues and you have to set up some machines, or you have to repair, fix some machines. Then after that, you do the quality control. QC stands for quality control. And then sometimes you have to fix some machines. And then you move into something called laser marking. and deburring, lapping, and then grinding, and final inspection of the final product. These are metallic products, and hopefully it goes into packing and is all done. So if I want to bottleneck analyze this process, I will move to the duration overview. I might want to try my chance both with median and with average. Median is very good because it's more outlier resistant, whereas average has a more intuitive representation. You can reason more intuitively about it. And I can what I will be looking for will be for the arcs first that take the longest time. It looks like it's this one. For example, this is a transition bottleneck. It takes, the median is 1.88 weeks, 1.89 weeks, which is pretty substantial if you consider that the median execution time of a case is 1.99 weeks. Probably, however, this case is very, very infrequent. So it's very good to try to analyze both the fact that something is a bottleneck, but sometimes also how frequently it is occurring. For that, you can click on this dual metric or secondary metric, and you are able to see both the duration, in this case, the median time between two activities, and also the number of times it occurs. In this case, only 2 times out of 225 cases. So I find here a situation where the transition bottleneck, the flow with the largest activity duration, is very infrequent. So I probably should not be worrying at all about it. So that's for the transition bottlenecks. The activity bottlenecks, so you have to look at the process map to see if you wanted to analyze the transition bottlenecks, you have to look at the process map. I'm going to remove all the filters, and you have to find which activity has the highest concentration of like highly weighted arcs attached to them. It seems like here is turning and milling QC. This is what we call the activity weighting bottleneck. Is the activity that is weighting the most. And I have, bear in mind that I have picked the total duration because the total duration captures both, is cumulative. So it captures both the amount of time it takes me to execute this activity per case, but also the number of cases where it occurs. So it's pretty good in terms of finding where I'm really having my waiting times overall in my process. Once I have that, I might want to concentrate on cases that contain that activity and continue my bottleneck analysis from there, possibly comparing the characteristics of cases where this activity weighting bottleneck occurs versus the cases where it does not occur. And in this process, you can see that the activity weighting bottleneck only has a processing time. It is very high waiting times, but it has a relatively small processing time. Let me put it on average to see it better. Turning and milling QC, you see that this activity actually doesn't take that much time. It takes 1.5 hours. So it is not the processing bottleneck. It is the waiting bottleneck. That's where most of the waiting time is located, but it's actually not the processing bottleneck, neither in terms of average nor in terms of totals. There are some other activities that are processing bottlenecks, like, for example, this one, that take 8.5 or 8.2 hours on average relative to this one. So it's kind of important when you talk about like my bottleneck to clarify, are you talking about the transition that takes the longest time? That is the transition waiting bottleneck. Are you talking the activity that for which I have to wait the longest? That's the activity waiting bottleneck. And or are we talking about the activity that takes the highest amount of processing time, and that is the activity processing bottleneck? And they can be different and in different locations in the process, depending on which one you're talking about. All three, of course, are important for different reasons. Activity waiting bottleneck, that is probably the place where you are lacking resources. Where if you wanted to speed up the process, that's where you need to maybe add resources into it. The waiting bottleneck, the transition waiting bottleneck, that is probably a place where you have a bit of a handoff problem. So one team handing off to another team is causing a lot of delays. So that's another place where you can go and reduce waiting times. And the activity processing bottleneck, that is the place where you could potentially reduce resource costs, because the processing time determines the resource cost. It is effectively proportional to the amount of person hours I am spending executing this task. And the number of person hours I spend executing a task, that is related to the cost of that task. So all three things are very important. It's also very useful to switch to the resource perspective and to redo the bottleneck analysis in order to find specific resources that are causing bottlenecks. And again, I can classify them into resource processing bottlenecks. So these are the resources that are doing the largest amount of work. The resource transition waiting bottlenecks, these are the handoffs that are contributing to a lot of waiting time in my process, where I might want to see why is it that this resource is not very efficiently passing work to the other. And of course, if the diagram was larger, I might want to be spotting a resource that is causing the largest amount of waiting times, where the sum of the arcs leading to the resource is the largest possible. Another way of looking into bottlenecks is by using the log animation function. So for that, I need to have a BPMN model, which of course I can export here. Let me put a BPMN model. Like I might not want to include in here all the activities, because a BPMN model with all these activities will not be very readable. I have seen even business processes that have 100, 150, 200 plus even 500 activities. So it's kind of good maybe before animating it to simplify it. Now, the standard way of simplifying is by removing the most infrequent activities, but beware. If my goal is to see the slowest activities rather than most infrequent ones, then I should abstract a little bit differently. In the abstraction settings, you can select abstract by average duration. And when you do that, the moment you start, this means that as you start moving your slider to the left, you are removing the activities that are the slowest. Well, that's not my intention here. It's the opposite. I would like to remove the activities that are the fastest. So now I use the invert ordering arc, and I'm gonna now start removing the faster activities, and I'm gonna leave the 25% slowest arcs, and maybe also only the 50% slowest nodes. So we'll reduce this one maybe even to 20%. And I get a diagram that is kind of more or less simpler than before. It only has about 20 activities, and it doesn't have much between them. And I export these BPMN diagrams. Let me just make it a little bit simpler because it's still a little bit too complex. It's kind of difficult to simplify this diagram, huh? Let me go for 25% of nodes. Okay, so I have 25% of the slowest nodes, and among those ones, I have 15% of the slowest arcs. I then export the BPMN model for it. I'll call it production model. And using a model like the production model and the log of the production event log, I can start now an animation. I play, and maybe I accelerate a little bit to bring it to a certain level. And then I can see now how bottlenecks will build up. I'll make it a little bit slower. And I can see here, how my bottleneck is building after packing and into this final inspection and waiting. Log animation gives you a bit of a complementary view. It allows you to zoom into specific tasks in the process and start seeing how the bottlenecks build up before or after a given activity over different periods of time, because here in the horizontal axis, I can choose, do I want to see the month of January or do I want to see the month of February? And it might be in some cases that in January I had some bottlenecks and that in February these bottlenecks were resolved. It's a more dynamic view on bottleneck analysis. The second thing I will do in the field of process performance mining is to do a workload analysis. Now it's a different perspective. So bottleneck is about where are you waiting or where are you spending time doing work. Workload is where are you busy, how busy you are, when are you busy, who is busy, in which activities I have busy resources. It allows you to identify overuse resource or underuse resource. One way of doing it is either in the frequency overlay or in the duration overlay. You will try to find activities that are either frequently executed or activities that in total take a large amount of processing time, and that the amount of processing time in total or the number of times that an activity is performed, that gives you an idea of how busy the resources are. The busiest resources are typically the ones that execute a large number of cases or that are involved in a large number of cases, or the ones that in total, on aggregate, they spend the largest amount of processing time. And I can see this in the process map, and I can also see a complementary view of this in the dashboard as well. Let me show you how these two things will complement. So I'm going to close this animation here. Go back to my production log. Here I can see the activities that are most frequently executed. That's probably one of the places where there will be the highest amount of workload in total. If I move to the duration view and I focus on the activities this time, and I use the total duration, which is the sum of the amount of time that I spent on each activity, I can immediately see the activities where I spend the most amount of effort. These are the activities where my workload is the highest. I can also switch to the resources perspective and see, are there some resources that are investing more time in this process than others? And I can immediately see that, yes, there are two resources here, ID 4794 and ID 4932, who are the ones where who are spending the highest amount of effort in this process. Those places where there is a highest workload are likely to be the cases that contribute to the largest cycle times. Let me have a shot at this hypothesis. The cycle time of this process, median, is 2 weeks. Now, let me remove those cases where this resource appears. So I right click, and those ones take less. When that resource is not involved in the process, the median execution time is 1.75 weeks instead of 2 weeks. So it's about 15% lower when that resource is not involved. Let me now do the opposite. And now in the filter, only retain those cases where this resource is involved. And what do I find? When that resource is involved, the median cycle time of the process is 2.27 weeks. So I compare the case where that resource has a high workload is involved and the cases where he is not involved. And I find that it ranges from a median of 1.75 when the resource is not involved and a median of 2.25 when it is involved. And I say, bingo, the presence of this resource is contributing by around 0.5 days. Is it days? No, it is weeks. 0.5 weeks to the execution times. The resource is not there, 1.75. The resource is there, 2.25. And I'm doing this on the median. If you look at the average, the effect is even a little bit more striking. So workload is a big contributor to waiting times. So just keep that in mind to direct your analysis. When you suspect that a resource might be contributing to workload, try to go to the resource perspective, set the duration overlay with an aggregation function of total so that you get a measure, a view on the workload of different resources, pick the resources with the highest workloads, and start comparing the process when this resource is involved with the process when this resource is not involved. And very likely, you are gonna, after doing this a few times, you are gonna spot some of the biggest contributors to your overall waiting times, because workload is the determinant of waiting times. I can do this in the performance dashboard, which gives me more like higher level overviews. So I can take this log and I can go to the resources view. And I can then see which resources are spend more time in the process in a histogram. So I see which resources are contributing most to the process in terms of times, and I can see also the frequencies of the resources, which resources are involved most frequently in the process. As usual, remember that you can take some of these charts, any of these charts, and you can edit it. And there are many more performance measures. When you pick resource on the x-axis, there are quite a few of performance measures that you can play around with on the y-axis. So you can see for every resource how much they contribute to waiting time, to processing time, etc. By building some custom charts in the dashboard plugin. So this, for example, we just saw that in the dashboard plugin, you can see this type of chart where for every resource, you get an idea of how much time they are spending in the process. And of course, the ones that are on the left-hand side are the overused resources, whereas those in the right-hand side are potentially the underused resource. Do keep in mind, however, that resources that are underused in a process are not necessarily resources who are doing nothing, because in real life, people are not entirely dedicated to only one process. People multitask. Resources in a process might be participating in different processes within the organization. So the fact that you have a resource that is underused according to this chart does not, or according to the process map, does not necessarily mean that this resource is not busy. They might be busy, but doing something else. So it's good. That's why workload is an indicator of waiting time, but you should not equate it to waiting time, because your workload in a process might not be reflective of your total workload as a worker in the organization. And that is why it is useful to look both at the waiting times bottlenecks, as we saw at the beginning of this lecture, and also look at the workload distribution. They will give you very complementary views on how busy or where your waiting times in your processes are. Bottleneck analysis, workload distribution analysis, they are fully complementary. So do both of them if you want to get a good grasp of the performance of your process. Workload is not the only thing that you should that determines waiting times. Another thing that determines waiting times is the demand. How many cases are being executed in the process at a given point in time? It is very often the case that a business process does not have a constant demand over time. Think about order to cash process in an e-commerce shop. December demand is very high. January, February, the demand is much lower than in December. So it is important also to look at the demand in your process, and that is something you can get by looking at this work in process, also known as active cases. And there is a specific chart in the performance dashboard in a Promore that will give you the distribution of active cases over time. You look at this diagram here and you can immediately look at the peak times. What am I going to do when I look at this? Well, immediately what I'll do is that I'll look at the cases that occur during peak times. I'll filter them out. Separately, I'll filter out the cases that occur in non-peak times, and I'll try to analyze them separately, possibly compare. If I am interested in typically waiting times during peak, then I will focus my analysis on the peak period. These periods that are between rectangles, those are the ones where I'm going to focus the most. Otherwise, if you try to do an analysis over the entire time frame of the event log, you will get a very partial view of the performance of the process, because some of the numbers are going to be diluted by this low season period where the number of active cases was very low. So we have seen that to analyze the performance of the process, you look at waiting times first. You look at those activities that have the highest waiting times leading to them. You look at the transitions and the handoffs that take the longest. Then you look at the workload of your resources. You try to see which resources are contributing the most amount of effort, because that's a determinant of waiting time. And then you look at the demand in order to identify periods of times during which there are more cases in your process. Those are the periods that are the most interesting to analyze in terms of waiting times. Waiting times is not everything we want to do when we do process performance mining. We also want to understand sources of waste, inefficiencies. One of the biggest sources of waste in a process is defect waste, when you do a mistake and you have to rework it. And so you cannot see defects in a process mining map, but you can see rework very clearly in many different forms. You can see self-loops, which are strong indicators of potential defects. You did an activity and then you had to repeat it. You see short loops from activity 1, you go to 2 and back to 1. Remember, those short loops might be a sign that there is parallelism between this activity, or it might be a sign that there is really rework. Watch out, go to the BPMN view to see if you see the rework in the BPMN view, because the BPMN view separates parallelism from repetition more cleanly than what process maps can do. And then sometimes you see like repetition involve a longer sequence of tasks. So we will be looking for all these 3 types of rework, like direct rework. Indirect rework, you do an activity, you quality check, you go back. Or you do an activity, you repair a defect and you go back. And also longer loops that might signal situations where you had a defect, you did a few other activities, and then you discovered that there was a problem and you came back. So let me do a bit of rework analysis of this process. There are 2 ways of doing the rework analysis. The first one is exploratory. You just take your process map, go to the activity view, and just try to see if you find some loops. I am seeing here some loops. The frequency view will be more telling in this respect. I am seeing some little loops here between quality control and fixed machine 15, between quality control and nitration quality control. So after this, I do that and then the other one. No, it's this one rather. Between turning and milling QC and machine 9. Just to be sure that this is not parallelism, but it's really rework, I'm going to switch to the BPMN view. And in the BPMN view, I'm going to see more cleanly what are the repetitions. Here I can see a repetition where you do turning and milling machine 9. Sometimes you move back. Actually, there is a double repetition here. This turning machine 9 is pretty problematic. You do it, and then sometimes you go back and you do turning QC and you might come back here. Or sometimes you go to milling machine 14 and then back to machine 9. So this task is quite problematic in terms of potential reworks that are happening. And I can see it both in the BPMN view and in the process map view equally well. Here I can see another repetition. Why? There is an XOR join. I do grounding machine 12. There is a split. Then sometimes I do a ground grinding manual and I repeat I go back to the loop that contains grounding machine 12, which means that I might be doing for those cases, I might be going through grinding machine 12. I discover that there is an error. I do round grinding manual, and then I put it back into the machine. So I do a bit of machine grinding, manual grinding, put back into the machine. Another way to do a rework analysis is, of course, by going to the filter. I'll remove all the filters and I'll create a rework and repetition filter where I can specifically sort the activities by how often they are repeated. And I can see activities that take sometimes a lot of repetition. Again, machine 9, but also machine 4 are popping up very strongly. So I might want to then focus on those activities, for example, where turning and milling where machine 9 occurs, say, more than 10 times. There are 6 such cases, and I can then investigate those cases maybe change the perspective, see who is involved, for which work order quantities are involved, etc. So I can look at other perspectives on these 6 cases to investigate why is it that I am having so much rework. Very often you will notice that when there is rework, if you take cases where an activity was reworked, the cycle time of those cases will be much longer than when the activity is not reworked. And by playing around with that possibility, you can find to what extent the repetition of an activity contributes to the total execution time of the process. So production, so I'm into rework analysis. I can do rework analysis by manually identifying backward transitions in the process map, or I can do it by means of the rework filter, or I can also simply go to the dashboard and look at the frequency of activities, and those activities that have the highest frequency are probably the ones that I will be taking as candidates for being activities that are being reworked. I will go back to my process map and I will try to look more carefully at whether or not those activities are inside a cycle in the process map. Try to then filter out those cases that go through that cycle and try to understand why could it be that these activities are being repeated, possibly by inspecting specific cases together with the domain experts. Finally, another type of very common type of waste is overprocessing. We say that overprocessing waste occurs when you perform an activity that was not necessary given the outcome of a case. And you say, how do I know that an activity was not necessary? Well, there are some indications of unnecessary activities in a process if you look at cases that finish early. Let me give you an example. If I start doing a process and the case is canceled, for example, because the customer withdrew their order, you have done overprocessing. You have done a lot of work and the customer canceled and it says like, wow, I didn't get the outcome I wanted. The customer canceled. All the work I did pretty much was reduced to nothing. Customer asks me for a quote. I give the quote and then I do not get an order. I have overprocessed. I have done work to give the quote and I didn't get the order that I wanted. So in a process map, you will see that there are some paths that lead to the end event through a long chain of activities. That is the normal path. And those pathways where I jump from the middle of the process to the end node, those are exceptional pathways. And to identify overprocessing, I will look at the exceptional pathways at these exits, and I'll try to isolate, to ask myself the question, why did I jump? What is the semantics of me having stopped the case in the middle? Is it just that the case is incompletely recorded, in which case I need to filter it out? Is it the case that the customer canceled? Or is it the case that we had to abort this process instance because, for example, the customer was not eligible to receive a benefit, for example, if this is a process for approving benefits for citizens? And if I find such cases, then I will see what activities I performed before I aborted or canceled the case, and that is going to allow me to quantify how much overprocessing waste there has been in cases that have led to cancellation or abortion of the process. Let me give you a concrete example. This is a purchasing process. I create a purchase requisition and I analyze the purchase requisition. I create a quotation. and I analyze a request for quotation. That means that I ask for quotes from suppliers. Suppliers give me quotes, and I analyze them, and sometimes I abort the case and I do not order. Why? Because maybe I decided I didn't need to buy this product. All this work you did to obtain quotes in order to, at the end, decide that you were not going to buy the product, that the case is aborted, that is what we call overprocessing. We want to know about it. We want, as process managers, we want to eliminate that, to reduce it. How can we avoid doing work for nothing at the end? Let me take that particular process. Okay, so in here, if I put it in full mode, I see that some cases are being aborted after the analyzed request for quotation. There might be two reasons for this. It might be that those cases have not finished, or it might be that, yes, they have finished. They were just aborted after analyzing the request for quotation. I determined that we should not proceed with that. So the first thing I will do is probably to then retain those cases where this abortion occurred, which are these ones. I might want to look at the time frame of those cases. Let me save this log, filtered. I might want to go to the dashboard, go to Analyze, View Performance Dashboard for these filter logs. Look either at the events over time or at the active cases over time. And what do I observe? I observe that such cases have been active during a whole period of time, even as far back as January. So it is actually, now that I look at it like this, it is very unlikely that these cases have not just finished, because I have seen them, that some of those cases, many of those cases have been active as far back as January, and we are currently in this log, we are already in October. So most likely, and they have been occurring over the whole period of time, these cases. So most likely, these cases have completed, but have been aborted. So now that I have determined like these cases have been aborted, let me try to quantify what is the effect of that abortion. So I can go, I can create a chart to capture the amount of effort that I have spent on these cases. I will take this case duration chart and I will turn it into a chart that will display, instead of the case duration, the total processing time of those cases. And this now gives me an idea. This chart here on the bottom right corner gives me an idea of how much, I have to give a name to this dashboard. Gives me an idea of how much effort I have spent on that process, doing work, sometimes 1 hour, sometimes 2 hours, sometimes as much as 4 hours of actual work to, at the end, not obtain, to at the end abort those cases. So it's quite substantial. No matter how I see it, it's actually telling me that that I'm spending a significant amount of time doing activities that I shouldn't be doing. They lead to aborted cases. So as a process manager or as an analyst, I will be recommending to establish more concrete policies or to redesign part of the process in order to reduce or to detect as early as possible that there are some cases that we will abort. the earliest I can abort the case, the less such cases I execute, the less overprocessing waste we are going to have in this process, the less we're going to do that leads to aborted or canceled cases. So 4 types of analysis we have seen. Bottleneck analysis, workload and demand analysis, rework analysis, and overprocessing analysis. The first 2 have to do with tracking waiting waste. The latter 2 have to do with tracking other types of waste, defect waste in the case of rework, and overprocessing waste in the last one. And if I do all this analysis, I can identify a lot of the sources of waste and inefficiencies in my process. So the right-hand side of this table gives you detailed instructions on what steps you can take in order to identify each of the 4 types of waste on the left-hand side. Once you have done performance analysis using the ideas captured in this template, it is good to complement that with some variant comparison, also known as variant analysis. For example, you can take those cases that have been on time, those cases that have been late, those cases that have high waiting time versus low waiting time, those cases where a resource with a high workload have been involved, and those cases where they have not been involved. And you can apply the 3 levels, variant analysis techniques to analyze the performance of those processes. When you are going to do variant analysis, which means comparing multiple subsets of cases, I recommend that you look at splitting your log in 3 ways. One is by performance, slow cases versus fast cases. Another one is logical. For example, you look at the attributes in your event log. Look at, do you have a type of customer attribute or something about the geography of the customer? Or look at, is there an attribute that indicates different product types or different product amounts or different outcomes, like the claim was accepted versus was rejected? Split your log according to these logical attributes and then start comparing the corresponding logs, the 2 separate logs, in order to understand why is it that, for example, in one geography, I am performing better in terms of waiting times or in terms of processing times than in another geography, or that for one type of product or one type of customer, I am performing better than for another one. And finally, I recommend also that you look at the log time frame in the dashboard, in the overview of the dashboard, and there you will find periods of times where I am busier and or less busy, and you carve out down some periods and separate the log into what happens in the low season versus the high season, and then you compare those 2 logs. In other words, when you do an analysis, after finding that there are performance issues, try to nail down those performance issues by cutting your log into slow cases, fast cases, different logical divisions according to domain attributes, and also temporal divisions of the log according to different periods of time, low season versus high season, and start doing a lot of comparisons. For example, using the 3 techniques we saw last week: comparison of flows, comparison of rework frequencies, and comparison of bottlenecks, both using the process map and dashboard, and possibly also animation. And I remind you from last week that we have a template for variant analysis that tells you, once you have divided an event log into 2 or more sublogs, compare them at the flow level, most frequent pathways in both logs, most frequent rework in both logs, compare them also in terms of handoffs on the resource perspective, and then compare them in terms of differences in waiting times or bottlenecks to understand why is it, that, for example, for some types of customers, you are doing something that makes you wait less than for other types of customers. That is where the insights for improving the process will come from this exercise of comparing multiple subsets of cases. So this is what I wanted to tell for today. Until now, we have been working on what I called as-is process mining, which means I am analyzing the history of my process, what has already been done, what is the current picture of my process. As I analyze that, I come out with ideas on how to improve it. For example, so I might sometimes want to say, what if I add a resource to the process? What if I automate a task? There's a task that is consuming me a lot of time, that is causing a lot of defects. What happens if I automate this task and as a result of it, I reduce the percentage of defects in my process and hence the rework in my process? And by the same token, I also reduce the processing time and therefore the workload of my resources. What will happen? What will be the cycle time if I do this change? By how much I will reduce waiting times in different parts of the process? These are the questions that we're going to answer next week, or I'm going to give you a method for answering them using a technique called business process simulation. And I'm going to show you how you can connect business process simulation with process mining in order to understand what is the impact of a change on the temporal performance of a process.